jumping into today as well. All right, so first up, what are our objectives? So for today, we're going to be solving linear inequalities with one variable, compound linear inequalities, absolute value inequalities, and then applications of inequalities. So first up, what is an inequality? How do we define it mathematically? Well, a linear inequality is any relationship in the form ax plus b greater than 0. If you remember when we talked about linear equations, we use the exact same symbols, right? The only difference is the inequality sign. So we have this case, we could have the less than case, we can do, variable. We could do the greater than or equal to, or less than or equal to. X is our variable, which honestly could be any variable, and then A and B are constants there. The solution to a linear inequality contains an infinite number of elements and can be expressed using set filter notation or interval notation. Okay. Set filter notation we've done before. Interval notation, that's the new stuff. Okay. So let me give you an example. So for set builder, that is this guy. Okay. Which we've seen. All x values given that or such that x is greater than or equal to -4. Okay, that's our set builder notation. Widely used in mathematics, and we do it all the time. Interval notation, I could take this exact same thing and rewrite it like this. Like I said, that one's a little bit newer. So let's talk about that notation, which we call interval notation. Okay? So to read interval notation, so if you just have parentheses, it means greater than or less than, but not equal to. Okay, so if you see just parentheses, greater than or less than, but not equal to. So for instance, this is not a parentheses, right? It's a bracket. So this isn't less than, okay? I'm sorry, it's not greater than. Man, I need to talk right. This is greater than just and equal to. Greater than and equal to. My gosh, my brain's still waking up apparently. If it was just a parentheses, let me just delete this for a second. It was just this, then what that means is it's greater than -4, but not equal to it. Okay? But with the parentheses, it's allowed to be equal to -4. Now notice this goes on forever, right? That's what this reads. It's -4 and just infinitely in that direction. That's what this is telling me here, that you're going infinitely in that direction. Okay? So then that means, we'll put the brackets here. Okay? So this means greater than or equal to or less than So this part in interval notation, this is talking about a greater than, okay? And again, it's equal to or not equal to depending on if it's a bracket or just a parentheses. On the right-hand side is our less than. Same principle. If it's a bracket, it's equal to it. If it's parentheses, it's not equal to it, okay? This is essentially shorthand for this guy. So you're gonna see both of those interchangeably throughout the whole entire lesson, okay? One thing I wanna put as an important note, okay? The infinity symbol will never have a bracket next to it. It can't be equal to infinity. Infinity is a behavior, right? That's what this is. It's a behavior. This is saying that the numbers just keep going on forever, so it's not a specific number. So you're never going to have a bracket next to it. Okay? So let's just apply. So let's look at some properties first, and then we're going to apply this. Sorry, I'm jumping ahead of my notes here. Okay. So let's look at some properties of inequalities. Which we know these properties already, we just might not have seen it written mathematically. So that's what this section is really going to try and introduce you to. So our first property, if some number is less than a, then we can say that a has to be greater than that number. We're just flip-flopping. They both mean the same thing. Nothing's changing there. Second property, if a is less than b, and b is less than c, then a is less than c. That, if you remember, if we just incorporate equal signs, okay, that is, oh, sorry, that's your, like, transfer property. Man, I can't write today. Third time's a charm. Okay, because, think about it, if a is less than b, okay, and b is less than c, then a has to be less than c, because it was less than b to begin with. So that's like your transitive property, just with no equal signs. Third property, a less than b, and c is less than d, then a plus c is less than b plus d. Okay? So in other words, okay, looking at this, a is already less than b, okay? C is smaller than D. So if I add C to this side and D to that side, it's still going to keep things the same. It's not going to change the value of the inequality whatsoever. Fourth one. A is less than B. Then A plus C is less than B plus C. And A minus C is less than B minus C. Now this is just your subtraction and addition properties of equality. If A is less than B, it doesn't matter what I add to those numbers or subtract, it's still going to remain less than each other. So it's, again, it's the addition and subtraction properties of equality that you learned back in Algebra 1. Okay, two more to go. If C is positive, and A is less than B, then AC is less than BC, and A over C is less than B over C. Okay? So this is your multiplication and division properties of equality. Okay, as long as C is positive and A is already less than B, it doesn't matter what I multiply both sides by, it's not going to change it. Doesn't matter if I divide both sides by it, it's not going to change it. Okay? The only time it would change is our last property here. Okay, if C is negative and A is less than B, then AC is greater than BC A over C is now greater than B over C. Okay? So if you remember, I'll just put it over here. Like if we had something like, 5 is less than 10, that's a true statement. But if I multiply it by a negative number, let's say just like -1 to both sides, well, that's a -5 saying less than -10. That's not a true statement. So therefore, I have to switch the inequality sign. That's what statement 6 is saying. Statement 5 says it doesn't matter if it was a positive 1, it's still going to remain the same. Or a positive 5, or whatever it is. That inequality won't change there. Okay? Let's take a look at an example. Solve the inequality. Graph the solution set. And write the solution set. And set builder. Notation. And interval notation. Okay. In other words, we're going to write the answers 3 different ways. That's what we're doing. So with inequalities, you were told, like kind of like in the past, still solve it like a normal equation. Like just pretend that was an equal sign. And if it was, what would you do? Well, I'd isolate the variable. So I'd add 3 to the other side. -7x greater than or equal to 28. Okay. And then afterwards we divide. Because I'm dividing by that negative, I have to change the sign. That's what this property is saying. So x is less than or equal to -4. And if you want to, I'll highlight it. Just to note that that was an important step. Easy to do when you're working with a bunch of these, like not do that. So graphing, well, here's -4, right? Now, in Algebra 2, I taught you like open and close dots. Well, those are gone now. I want us to look at this guy over here. We're going to use parentheses or brackets, okay? So notice, there's an equal to sign. Therefore, I'm going to use a bracket, right? If there was no equal to sign, I'd use a parenthesis. So I'm going to use a bracket, and I want less than, so that's in this direction, right? So what I'm going to do is I'm going to put a bracket here, okay, to indicate that, and then just draw an arrow in the direction where all my answers are. Looks like a backwards E, huh? Next, set builder notation. Well, all x values such that x is less than or equal to -4. So there's that guy. Okay, last notation, interval notation. Okay, so x is what? Less than or equal to -4. Okay, so that's going to be here. But if I go in the negative direction infinitely, that's this guy over here. Okay, so it can equal -4, but it can't go past it. This is like your largest number it can be. And then it keeps going in this direction, so it doesn't stop. That's when we get the negative thing. So all 3 of these are equivalent to the solution set here. And you can always check your work, right? If you just plug any number in, like -5, -6, plug it into here, it's going to make the statement true, which is why it's an infinite solution set. All right. Any questions on this? This is going to take a little bit of time to get used to. Okay. Let's try another example. We're going to solve the inequality. And we're going to do the same thing. I'm going to write it 3 different ways just to get some practice with it. not an inequality, but changes to an equal sign, we've seen that. And one of the things we try to do was to knock out the fractions, right? We multiply by what we call an LCD. So the LCD for this guy, okay, is going to be 8, right? That's the least common multiple for 2 and 8. So multiply this by 8 and multiply this side by 8, okay? So 8 divided by 2 is 4, so I'm going to multiply the numerator by that. Over here, the 8's are going to reduce, so I'm just left with the numerator. Multiply these two together, I get 40. Oh, I'm so used to writing equal to, huh? Sorry about that. So less than or equal to 40. We'll distribute. Okay, and just start combining like terms, right? So the 4 and a 3, that gives me a 7x. Negative 8 and a 1, so minus 7. So we're getting closer here. We'll add 7 to both sides. And then last step, divide. So x is less than or equal to 47 over 7. And it's okay to leave it like a fraction. Just make sure it's a reduced fraction. I think a lot of times we're so used to math problems just coming out to be like a nice answer, right? Like the answer is 2. And that makes us feel happy. It's like, okay, I did it right because I got an integer answer. But fractions, they're acceptable as well. Okay, number line. I'll put it over here. So I'm just focusing on the 47 over 7. If you want to include other numbers, you can. So it's going to be less than or equal to. Because it's an equal to symbol, I'm going to have a bracket again, and then an arrow indicating the less than part. Okay? Really does look funky, doesn't it? I think that kind of proves the point that when you get further in mathematics, you don't really graph the solution set like this. You just keep it as set builder or interval notation. So next, set builder notation. So it's x, right? Yeah, all x values, given that x is less or equal to 47 over 7. So we can represent it in this fashion. Or the last case, so this is my largest value because x has to be less than that. So that's going to be on the right-hand side. Whoa. Try that again. Okay, and it's going infinitely in this direction, so infinitely in the negative direction. And we're putting a parentheses there because you can't equal infinity. Again, it's more of a behavior, like where are my answers going? It's not a solid number. Okay, so there we go. We have our one variable inequalities, and we had some practice using all 3 different ways of representing the solution set. Let's jump to compound inequalities. Quick definition. Statements with 2 or more inequalities joined by the word and or the word or are called compound inequalities. Okay. And I mean, we know what these look like anyway. Again, it's just seeing if you can recognize and just getting you used to the mathematical definition of it. Okay? So let's just jump to an example. So we're going to solve a compound inequality, and this one's going to be an OR inequality. Okay, so we're going to solve OR inequality there. Well, if you see an OR, that's telling me that I'm gonna have to solve these separately at first, and then see what the answer is gonna give me. So on this side, I'm gonna add the 7, so 2x less than or equal to 16. We'll divide, we get 8 for that. Okay. On the right-hand side, what do we have here? Well, to get rid of the fraction, I'm gonna multiply both sides by -3. Now when I do that, we know the symbol has to change. So if I multiply this by -3, I just get an x. It is now greater than, multiply this by -3, I get a 12. And then I don't want to forget the or in between there. So think about it visually in your head. So what this is telling me is x has to be larger than 12 for these to work, or x has to be 8 or less than that. So that means, if I'm visualizing this on a number line, there's a space in between those two numbers that I'm not using on the number line. There's a whole section of values I don't want. Okay? So visually, looks like this. So here's 8. Okay, here's 12. Now for the 8, it is an equal to symbol, so it's going to have a bracket. And it goes in that direction. All those values. On this side, okay, same thing, except now I'm going to use a parentheses, okay, indicating that it can't be 12, but I'm going to indicate with an arrow that it has to be all the values that are larger than that. So there's the visual. Okay. Now, set builder. All x values such that x is less than or equal to 8, or x is greater than 12. That one's easy, you're just kind of rewriting it, just putting it in the parentheses there. Now, interval notation, okay, that's gonna look a little different. Because it's an or statement, I can't combine both of them into one interval, okay? It's just impossible. So that means I'm gonna have 2 intervals, okay? So let's focus on this interval here. It could be 8 and everything less than that, right? Okay? So underneath it, I'm gonna write what this is. So it's 8, comma, negative infinity. Okay? So again, 8's the largest, that's always gonna be here. Bracket, because it can include it. And then everything less than that. On this one, okay, 12 is the minimum, right? But I don't want to include it, so it gets a parentheses, and then it goes positive infinitely. So I'll just put just a normal infinity sign, and another set of parentheses because again you can't equal it. Okay. Now, I don't want to leave them separate like that. I want to put them together. So what we do is we use a union symbol, which is just a big U in between. So now that we have these written, let's incorporate it. I'm out of space here. I'm going to put it up here. So the interval notation for this guy is going to read as follows. Okay? So this is the number lines, it's this, they're all equivalent to each other. So this is telling me 8, including 8, and less than that. This is saying 12, but not including 12, and greater than that. Okay? Now, just to point it out there, could you have another interval thing? Absolutely, right? You could have multiple of these. All you would do is be connecting with U, which is our union symbol. I'll put that underneath. So this is the union, meaning it's this or that. Okay. Let's try an and. So that's an or inequality. Let's try an and. So even with an and, like sometimes we actually see this condensed into one inequality, right? It can still be separated by an and inequality. There's nothing wrong with that. you're still going to approach it with an or where you just solve each one individually. Okay? So for this one, that's not too bad. I just have to multiply by 5 over 2 to both sides. Just have enough space for it. Same thing over here, multiply by 5 over 2. Okay. These reduce, I just get n. Greater than, so 8 times 5, that's 40, divided by 2, so that's 20. Okay. Now, on the other side, I'm going to go ahead and just divide by this, and, oh, I missed a negative sign. My apologies. Yeah, there's a negative right there. Okay, so that should be a negative 0.5n. We'll divide both sides by negative 0.5n. Now, when we do that, that does switch the sign, so now it's greater than or equal to, and it would be a negative 18 there. Okay? Now, this one's a little bit different. I'm going to show the graph for this one so we can understand what's going on. But you might see it already. Because it's an and, your answers have to satisfy this and this, right? Have to satisfy both. Well, this one says greater than negative 18, this one says greater than 20. So is there a space of numbers that both of these are not working for? There are. So let's look at this guy first. Okay, so this one says 20, okay? And just a parentheses, because you don't want to include it, we're going in that direction. Okay, this one says negative 18, a bracket, because we want to include it, and we're going in that direction. So visually, if you can see, until I get to 20, this range of numbers is only working for one of these, right? I want it to work for both. So for them to work for both, well, isn't this eventually going to hit 20 and go beyond, just like this is? So therefore, the only solution set for this guy is when n is bigger than 20, okay? Because visually we can see that negative 17, negative 16, negative 15, 0, 1, 2, 3, that only works for this. But because it's an and, it has to work for both. But this will eventually overlap with this guy where they're both good for each of these inequalities. So that's why I'm only considering this as my solution set. So for set builder, it's all n values such that, or given that n is greater than 20. And then in set builder, it's even easier. It's just the comma, because we don't want to include 20, and it goes infinitely in the positive direction, which, again, parentheses, because we don't want to include infinity, because that's not really a number. Okay. Cool. Let's do a 3-part inequality now. Let's take a look at this guy. So 3 parts because, well, it's got 3 parts, right? 1, 2, and 3. Now this is an and inequality. I just didn't separate with the word and, it's just kind of all condensed together. So what am I going to do with this? I still want to get rid of the fraction. Okay, so to get rid of that fraction, I'm going to multiply everything by 2. Not just this, but also this guy. So this gets a 2. Well, this gets a 2. And on the right-hand side gets a 2. So this becomes a negative 12. This is just negative 4x plus 1 because the 2 is reduced down. And then 2 times 5 less than or equal to 10. That's a little easier on the eyes. Now, for solving it, if I were to block this part out, your next step would be to subtract 1, right? Well, because I have this extra piece here, I have to subtract 1 from this side as well. It keeps things in balance, doesn't change the value of the inequality when we do that. So those are going to cancel out. I'm left with negative 13. And on this side, I'm left with 9. Okay. Last step, divide by negative 4. this is going to change the signs, the direction of them, okay? It's going to look a little funky right now. So this is just going to become a 13 over 4 positive. Okay, this is going to switch to this guy. This is just going to be an x. That's going to switch, and this would be negative 9 over 4. Okay? Now again, that looks a little weird. Typically we have what, the negatives first and the positives afterwards. So what I'm going to do is just swap this around. So negative 9 over 4 less than or equal to x less than 13 over 4. So that's what I'm going to do instead. Just flip them around to where it's a little bit normal to read that inequality statement. Okay? Now, I'm not going to go through every one of those. Let's just go ahead and use interval notation because that's a lot newer to us. So writing this answer in interval notation, it's not going past this guy. So we'll use a comma or parentheses, not a bracket because we don't want it to be equal to it. And then this would be a bracket because we want it to be equal to it. And then negative 9 over 4. Okay. All right. Cool. So, doing good so far? Let's bring absolute value in this now. I think my eraser needs oil. Kind of squeaking. At least it's erasing a little bit better. I don't know if you guys saw last week or even the week before. I mean, this whole board was just cluttered with stuff it wouldn't want to erase. And Windex works. Imagine that. Windex did a better job than Expo Marker Cleaner. So let's just do a quick recall. Let's say I had something like this, right? Now remember, absolute value is how far you are from 0, like how many units, okay? Well, this is less than 4. That's saying, okay, that we want numbers whose distance from 0 is less than 4 units. Okay, that's what that's telling me. And we could think of some right now, like 3 would work, 2 would work, 1 would work, 1.7 would work, okay? But we also have to consider the other side of the number line, right? Negative numbers can satisfy this as well. So if I were just to graph it visually for a moment, so here's 4, here's 0. So we know all of these numbers are going to be less than 4 units from 0. But if you look at the negative component, negative 1 is only 1 unit from 0. Negative 2 is 2 units from 0. That satisfies this all the way up to negative 4. So all of these guys right here, okay, would make that statement true. So how do we access that other side? Well, we know this part of the inequality is just this, less than 4. But the other side, to get these negative numbers, we want x values that are greater than negative 4 here. So that means that when we're solving for absolute value inequalities, that no, I have to include this case, but I also need this case as well, where I switch the direction of the sign and change the value that's across from it. Okay, so those are 2 very important things that we have to consider when looking at absolute value inequality. We have to consider the simple case, but also the other side of the number line where some of that stuff could also satisfy. Okay, does that look a little bit familiar from last year? All right, so let's look at some properties, and then we'll apply. So properties of absolute value inequalities. For a real number, k greater than 0, first property, absolute value of u less than k is equivalent. Can't write with 2 markers in my hand. Wasn't working there. less than u less than k. Alrighty? So what's that talking about? Well, that's this case up here. Okay, an example to go with it. U is our variable x in this case. K was 4, okay? So notice, is this an and inequality statement that I'm looking at here? It is. And that's what this is saying here. If you have this that comes up, it's the same thing as writing it as an and inequality statement. Now, let's look at the other case. Let's say it was greater than k. Well, it's kind of the opposite. So that's equivalent to u is less than negative k or u is greater than k. Okay? So again, if I were to switch this, like change it to a greater than 4, okay, then my number line of what I'm coloring in is what are potential answers is going to switch. So I'll put that underneath here. So if I had this, okay, well, numbers that are larger than 4 units away from 0, that's all this stuff. And then, of course, I got to consider the negative implication. All these negative numbers are greater than 4 units from 0. So there's my or implication there. All right. So far, so good with that. Now, do you have to memorize stuff like this? I don't. To me, when I see something like that, I either visualize a number line or make the changes myself to see it, okay? But what this is doing here, again, it's just showing you what's a mathematical way of writing this guy up here. All right. So let's try solving one. Sydney? No. Yeah, that's okay. Yeah, over here. Okay, solving an absolute value inequality. So there's our next example. Always get the absolute value by itself first. It's hard to evaluate what the distance is yet until this is by itself. Because right now, what's it saying? What's the negative 35? You can't have negative distance, right? So it doesn't make sense as it is. But when we simplify this part, it will become something that makes sense. So I'll divide both sides by negative 5. And when I do that, that's going to change the symbol. So I get x minus 4 is now greater than or equal to 7. Okay? Now this is easier to read. This is saying that this number is from 0 is larger or equal to 7 units. Okay. Now, just like what I just said over there, I'm going to have one situation where I'm looking at the positive end of the number line, like on the right-hand side, and then I'm going to consider the other where I have to switch the sign and switch the value of the value across from it. What the heck? Let's highlight that. That way we know that that's important. Solve each one individually. In this case, I'll add 4. I'm still adding 4 over here, which would make that a negative 3. Okay. Now, this is where I said I don't really memorize that over there. Visually in your head, you have x is bigger than 11, so that's this direction. X is less than negative 3, that's this direction. There's nothing in the middle, right? None of those numbers work. So that means we're looking at an or situation, right? Okay. Originally in the beginning, look, this is a greater than, that's a greater than, it says it's an or, but again, I'm not a fan of memorizing stuff like that. To me, I could visually see in my head on a number line if it's an and or an or. Okay, I want to put this in interval notation just to practice it. This one over here, well, negative 3 is the highest, and I can include it. And and then it goes negative infinity in that direction. This guy, okay, I want it to be bigger than 11. So 11 is the smallest I got here, but a bracket because I want to include it, and then positive infinity over there. So now I got two intervals. I want to combine them into one. So I'm going to use the U for a union. So here we go. I'm just going to rewrite it here. Union with negative infinity. Oh, I did that backwards. Negative first. So negative infinity, negative 3, union with 11 infinity. Yeah, when you do interval notation, the order doesn't matter. The negatives are going to come first before the positives there. If you flip-flop it, it doesn't quite work out too well there. What do you think? Still on board? Still doing good? All right. I want to look at some special cases, and then we'll do an application, and that'll be it. So, special cases. What happens when it's not that? Okay? So, absolute value, inequalities, special cases. So, first one. Well, is that a true statement? Can that actually happen? No. Can you have this distance from 0 less than 1,000 units? No, that doesn't make sense at all. So this is a no solution. So no solution, therefore just empty brackets, right? Empty brackets mean no solution. But it's so easy to your mind's just going, you're like, okay, I know what to do first. I'm gonna set up two equations and go from there. Just pause and look to see what this is first. Okay, next special case. Another instance where you don't want to act immediately. Think about what is being said. The distance this is from 0 is greater than or equal to negative 4 units. Is this always going to be positive? Yep. Is a positive number always going to be larger than negative 4 units away? Yeah, it doesn't matter what number we use. Okay, this is an all real solution. But how do we write that in interval notation, right? Well, it's simple. Use the infinity symbols. Okay? That indicates right here that it would always work. So all real solutions. And that's how you write it with interval notation there. Our next special case. Now, if you look at part A, negatives weren't good. You can't be less than a negative distance. But look at part C. This is kind of implying that in a little bit, right? It has to be less than 0 units. That's not good. But it does say it's allowed to be equal to, right? Because of that, I have at least one case to consider. When is this equal to 0, right? But it can't be less than 0. So only one case to consider. So this is really looking at just this. That's all I can do, okay? So solving it, I get x to be 10, okay? And if you plug it back in, it works, right? 10 minus 10 is 0. Absolute value 0 is equal to 0. So this only has one solution. Okay, so that's your solution set. All right, last one. It's almost the opposite of part C. If you look, I want numbers that are greater than 0. The distance is larger than 0. Well, the only thing you have to worry about is what if this is equal to 0, right? If this is equal to 0, would that satisfy this? No. So that's the only thing we have to worry about. So here, when is x minus 10 equal to 0, right? Okay. And the other thing we have to worry about is, and actually I'll write it using the definition. So when is this greater than 0, but When is this less than 0? Okay? Because again, I don't want to include 10 in any of this, because 10 makes that 0. That's no good. So on this side, x has to be bigger than 10, which makes sense, because if I plug 11 in, that works. 12, 13, 14, we're good. On this side, to consider the negatives, x has to be less than 10. So if I plug 9 in, that works, because it's -1, which becomes +1. If I plug in 8, 7, 0, whatever, that's always going to be true for this guy, okay? So therefore, these are my solution sets. I just can't include 10. How do you write that interval notation? Well, it's going to be a union, because this is saying bigger than 10, which is this direction. I'm sorry, less than 10, which is that direction. My brain's not working today, I'm sorry. And greater than 10, which is this direction. So an interval notation looks like this. So -infinity to 10, just not including it. Union with, there we go, 10 to +infinity. So there's my interval notation. Notice no brackets around 10, because we don't want that to happen. All right, let's apply. Oops. Sarah has test scores of 98, 84, 86, 92, and 89. Her score for online homework is a 99 and is weighted as 1 test grade. Kind of odd, but yeah, that's what the teacher decided. So Sarah still needs to take the final exam, which counts as 2 test grades. What score does she need on the final exam to have an average of at least 92? Okay. Now they're not telling me how these are weighted, like this is worth 50% of their grade or whatever. So I don't have to worry about multiplying by weights here. I could just jump right into a point system. They're just telling me that this is going to be 1 test grade. Okay, they're telling me the final exam is worth 2 test grades. So we're just going to worry about that. We're not going to have to worry about multiplying by weight. Well, if I want to find the average of anything, I add up all my scores, divide by how many there are, and see what the average is going to be. But I want the average to be bigger than 92, okay? Or equal to it, because that at least part allows me to have that happen. So let's add everything up. So 98, 84, 86, 92, 89, 99. Can't forget the online homework. Now, the final exam is 2 test grades. Well, let's let X be the final exam. And because it's worth 2 test grades, we're going to put that as a 2x there. Okay, so we're going to double the final exam score. So if I count these up, 1, 2, 3, 4, 5, wait, 1, 2, 3, 4, 5, 6, 7. Am I missing one here? 98, 84, 86, 92, 89, 99. Oh, 8 because the exam is worth 2. I was going to say, wait a minute, am I missing a score there? No, I'm not. So we're counting it as 2 there. So yeah, it'd be a total of 8. So we want that to be greater than or equal to 92. And this is something I'm sure you guys have done in the past too. Like, what grade do I need to achieve my A, right? Like, what grade do I need on this exam to get to that point? Okay, now we just gotta what? Add everything together on top. So that gives me to 548 plus 2x over 8 is greater than or equal to 736. Now to get rid of the fraction, multiply both sides by 8. Okay, so we get 548 plus 2x greater than or equal to, well, yeah, I can't copy down things right anyway, can I? Sorry, that's a 92 and that's a 736 there. It's a Monday. Definitely a Monday feeling. So we'll subtract the 548, divide by 2. And her final exam grade has to be 94 or larger than that. Okay? So again, it's an application of an inequality, just to see how you would use it there. If there were weights attached to this, I would multiply, like what I would do is take the average of homework, multiply it by the weight. Take your average of your tests, multiply it by the weight. And I would add those together, okay? I wouldn't have to take the average of it, I just add them together to see if I can get them larger than or equal to 92. Okay, so let's try an absolute value application to finish this up. Last one. I figured I like coffee, let's do a coffee problem. A coffee machine is calibrated to keep coffee dispensed at a temperature of 130 degrees Fahrenheit with a measurement error of no more than 3 degrees Fahrenheit. Okay? So we're going to do 2 things. Part A, we're going to write the absolute value. And then part B, we're going to solve it and interpret the answer. I don't know what coffee's supposed to be in. I don't know if 130 is too hot or not. I don't really measure the temperature of my coffee. If there's a barista in here, maybe you know. But I have no idea. So I don't know what the temperature of my coffee is yet. But I know that it should be at least 130. So what I'm going to do, we're going to let X, okay, be the temperature of your coffee. Because you have a thermometer in your pocket. You carry that with you. Why wouldn't you? So we're going to take my temperature minus the temperature it should be. And you don't want it to be more than 3 degrees difference. So we'll put less than or equal to 3. So again, we want our difference from the actual temperature not to exceed this guy. Now we're just going to solve it. So we have 2 cases to consider. The first case, you don't change a thing. Second case, I change the sign, the direction of the sign, and the sign of the constant across from it. And solve each one. So this would give me 133 degrees. And on the other side, that would give me 127 degrees. Now think about it before we finalize the answer. Could I determine this without creating this guy? Absolutely, right? If I were to add 3 degrees and subtract, I'm going to get those ranges anyway. What this problem is testing you is to see, can you use the definition of absolute value to create something like this that represents a situation? That's what it wants it to do. So to finish it, my ideal temperature is between 133 and 127.